Great. Well, thanks everyone for coming, and I'd like to thank the organizers for inviting me. I think of my role this morning as sort of provoking discussion of the sort of vast menu of topics that Sean covered in yesterday afternoon's talks. And since this is such a hard audience to provoke discussion in, I'm sure I have a very hard task ahead of me. So I've just selected some of the things that were discussed in Sean's talk, and some of it will be repeating some of what Sean said. I hope it's not too boring. Some of it will be a little repetitive, but I'll have sort of different angles on some of the same issues. I want to start by saying, though, that I think there's a sense in which the debate goes to a very fundamental question about what the aims we might have for cosmological theories are. And this is a historical debate that Ernan McMullen, for example, describes as going back to discussions among Epicureans about how you could have a theory of the universe. And I think there's two very different aims that different people have for cosmological theories. One is that we should seek a theory that's indifferent to a particular choice of initial states, or is independent of any claims about initial conditions. And so this is, for example, the Epicureans thought you could have an atomistic theory in which you had order arising out of chaos, all by virtue of mechanical laws. And this is something that Descartes also proposed. So this is an old idea that you could have order arising just by the dynamics. I think there's a different way of putting that in, which is maybe more in line with what we're seeing in contemporary theories, is that a natural initial state is an equilibrium state. So again, you'd have, with an explanation starting from equilibrium, you have a kind of independence of further details. So I think of that as being similar in spirit, although you're still making a claim about the initial state, that it's an equilibrium, and then you can understand things as fluctuations away from that. Now, I think there's a very different approach, which is to just say that we need to postulate a specific initial state. So this can take various forms. You could imagine just saying we're going to accept it as a contingent brute fact that there was one state that the universe happened to actualize. You might think that you have a theory that forces you to choose a particular state that's not really a dynamical theory but has a different character, a theory of initial conditions. Or there might be a special postulate, such as the past hypothesis, which you think specifies an initial state that you have to assume maybe a sort of a transcendental condition on other aspects of your reasoning. So I think these are very different aims for what a cosmological theory might look like.
Sorry, I just started the discussion already, but if those are supposed to be a comprehensive list of the possibilities, I would say that what I'm aiming for is a non-equilibrium solution that does not presume special features of the initial state. The fact that there is no equilibrium is crucial.
Right, so I didn't mean to collapse these two. So I would think of that as following something like the dynamics sufficient to produce without presupposing an initial state. I didn't mean this to be comprehensive, but yes.
Yeah, just to make a quick point. If you look at not the formation of the whole universe, but rather the formation of a planet or a star or a galaxy or anything in our universe, in other words, where we can actually measure the initial conditions, it never starts from equilibrium. The interstellar medium is notoriously out of thermal equilibrium. Star formation happens from a non-equilibrium state, and so forth. So it's not clear to me why it's not obvious that you need an equilibrium state, because everything that we can actually measure starts from a non-equilibrium set of initial conditions. Just in all the cases we can measure it.
Right.
Well, no, but in defense of reference to equilibrium, the standard Big Bang theory, the hot Big Bang, everything is in equilibrium at sufficiently early times, though earlier.
Oh, I'm not saying that we
and
can't
then
do
the
that.
whole,
I'm only saying that...
No, but the whole interesting story, as I explained in some detail in my lectures last week, is a series of different parts of the universe going out of equilibrium. So just as you say, all the interesting structure formation, every single bit of it is decrease in entropy. It's always dropping out of equilibrium, radiating away, decreasing entropy. The big story is not low entropy initial conditions. That's of course necessary, but trivial. The big story is how entropy gets lost. That's what actually happens. As things go out of equilibrium, so that's what real astronomers doing real calculations really do.
Right, yeah. So I didn't mean to be saying that that was not part of cosmological theorizing. So maybe I should say aims for cosmological theories in dealing with the initial state or something more specific. I'm thinking of specifically questions about the initial state and not initial states of subsystems necessarily. So you could have, for specific systems, you might, your environment will lead you to not being in an equilibrium state.
No, but still,
Yeah,
I
no,
think the point you were trying to make is a valid point, namely that at some fairly early time, before the phase transitions that drive things out of equilibrium, but after, there is supposedly in the standard picture an equilibrium. And equilibrium means that you hide a lot of the details of what came before. And
Right.
if that was the point you were trying to make, that part
Yeah, no, that
is part of our standard story.
Yes.
Well, sorry,
Can
it's completely not part of the standard story. The early universe is rapidly expanding. It's changing dramatically. Equilibrium states are static.
Okay,
No, I
so,
think that's
so there's a question of whether you're talking about local thermal equilibrium or equilibrium in some different sense. So David and then Anthony.
Oh,
You had your hand up.
yeah, gosh, but the discussion is all over the place. My point is about something else. Maybe I'll just say it very briefly. Anything can happen. This is just really about terminology on the bottom of your slide here. There's a long debate in philosophy, which there's absolutely no reason to start going into now, about what it is to be a law of nature. And there are various important camps in this debate, according to which a stipulation of something like an initial state of the universe, the sort of Jungian camp, in which something like an initial state of the universe would count as a very important fundamental natural law.
Yeah.
Not a brute fact or a special
Yeah,
postulate.
I was
Right.
planning to come to that.
Oh, okay,
eventually,
good, I'm sorry. Good,
yeah.
good.
And Anthony, sorry.
Yeah, so I just wanted to take a minute to talk about entropy and some of the things that Joel's been talking about, because I think it's crucial to distinguish between sort of thermodynamic entropy of the fields and particles in the space-time and the space-time degrees of freedom, or the gravitational degrees of freedom, because they behave very differently. And I think the right way to think about just the early part of the hot Big Bang cosmology, through nucleosynthesis and things like that, is that, if you were to halt the cosmic expansion, or certain processes are in equilibrium because they happen on time scales faster than the cosmic expansion. And you could think of this as saying that in terms of those processes, you have kind of a box and you've got this hot gas and it's in equilibrium. But in reality, the universe is expanding and that box is simply
Right, so
getting
they fall
bigger.
out of equilibrium.
Right,
Yeah.
so the maximum entropy state in that box, subject to some finite energy, is getting bigger. So you've got a bigger gap between the actual entropy and the maximum possible entropy. And that represents the structure, the interesting structure that you're forming, like interesting nuclei and later,
Right.
Other interesting stuff. So I think but what's very important, I think, are two things. One is that there's secretly this changing set of macroscopic constraints on the particles and fields that determines what their equilibrium configuration is, and that's changing with time. So they never manage to get into, they keep falling out of equilibrium, as Joel said. Second, that I think it doesn't seem to be widely appreciated that gravitational, it's important to keep in mind that gravitational processes that are increasing entropy tend to increase inhomogeneity, decrease homogeneity, which is the opposite of most thermodynamic processes, but it's crucial to keep in mind. And what's hard about this is that there isn't an actual calculation behind taking just some arbitrary, non-uniform gravitational field and ascribing an entropy to it. But we do know what it is in terms of black hole static configurations. We do know what it is in terms of gravitational waves, where we can treat them essentially as particles and kind of count. But in between, it's clear that it has to be the case that more inhomogeneous gravitational systems are higher entropy.
But Anthony, isn't it just for sort of pedagogical purposes, you can make that very plausible just from Newtonian gravity.
Yeah, yeah. I mean,
That the higher entropy, that by the ordinary Boltzmannian phase space calculation, the entropy is getting higher by clumping because you're getting more of a spread in momentum space than you're decreasing the spread in position space.
no, absolutely. So I think there are all kinds of suggestions that gravitational entropy goes up
Right.
with more inhomogeneity.
Right.
There just isn't a agreed upon definition by which you can calculate the entropy of an arbitrary gravitational field. But I think you have to be careful in statements like some of the ones that Joel's making, that entropy goes down in, some self-gravitating system, because it's true that it's giving away some entropy to radiation, but it's also true, I think, that it's gaining some gravitational entropy from making an inhomogeneous metric, and it's not at all clear to me which of those is in fact winning. It's also not clear whether it matters. So I think there are a lot of arguments that get confused because of this confusion between types of entropy, like the horizon problem. People have an intuition that as you get, if you just had time to get the gas in equilibrium, you could explain the uniformity of the CMB, and that's not true, as Sean said, because the real problem is that the universe wants to get more inhomogeneous rather than homogeneous as entropy is going up, if you include gravity. So sorry, that was a long dive.
Yeah, no, that was so that was very helpful. I think I probably radically misstated what I meant by equilibrium.
This is not even at all
right,
a response to that.
Okay,
This is completely unprovoked assault.
like I said, I think it would be very hard to provoke discussion with this group. So, but let me say so here's an example which I think is an articulation of the first point of view. And I'm just curious how many of you think that you would agree with a claim perhaps suitably clarified of this form. We must find some way of eliminating the need for an initial condition to be specified. Only then will the universe be subject to the rule of theory. This provides us with a criterion so compelling that the theory of the universe which best conforms us to it is almost certain to be right. So are there any takers? Anyone who finds that sort of argument compelling?
If you replace must by should try to,
okay.
by
Yeah, it's quite strong.
must is pretty hard.
Yeah.
I'd like to.
Okay, you would.
I think it's important.
Okay. Okay, good. This was Dinesh Sharma writing in 1959 about the steady state theory. So obviously, he shortly recognized that there was also the question of whether the theory has correct predictions that was perhaps more important than whether it conforms to this idea. But I think there's actually an intuition or an aim expressed here that seems to be captured by, say, steady state eternal inflation. So I think this is an aim that is shared. Yes, Anthony?
Just a quick note on this. Something that's interesting, I think, about this mode of thought is that there's an idea that they had, and I think some people thinking about eternal inflation had, that if you had truly eternal inflation, all the way backward in time as well, that there would be no initial condition, and somehow it would define itself. And I think that's just not true. When you actually construct those theories, there's a boundary condition. It's just not an initial condition.
Right.
So I think we now understand, I think, what the boundary condition is for the steady state universe. And, there is this very specific boundary condition that obeys. It's just not at a time.
Right.
And that's, I think, an interesting twist on this debate.
Good. Yeah, I was actually going to go to that topic first. So I was going to start off with just a discussion of what we can say about whether the universe needs an initial state. And actually, Anthony, one of your comments earlier at the conference about differentiating between the Big Bang model and the claim that there is actually a Big Bang singularity is, partly what I'm going to be focusing on there. Then I'll go on to look at discussion of theories of the initial state, and then sort of go back to the dialectic that Sean was talking about yesterday, about the sort of old way of motivating inflation, and then the shift to looking at eternal inflation. So let's start then just with this question: does the universe have an initial state? Or I think a better formulation is the universe finite to the past? And the arguments that people have given that it should be finite to the past. So you can start with, in the early days of relativity, people looked at the FLRW models these maximally symmetric models that you all know give a very simple description in terms of two equations for the scale factor and how it evolves over time. And if you extrapolate backwards in time, the scale factor goes to 0 in those models, and the energy density as a function of t cosmic time goes to infinity within some finite time. You have to make some assumptions about the energy and matter distribution in these models. Yes?
This actually relates to what Anthony just said. You were equating on your last slide, stipulating, I forget exactly how you put it, stipulating an initial state or equating, stipulating an initial state with the finiteness toward the path. What Anthony just said, and more generally, those aren't necessarily equivalent.
No, I didn't. I thought that the second was a better way of stating the question than the first. Partly because you can say that the universe is finite to the past without saying there's any. It's like you can't say that there's a number closest to 0 on the real line. Similarly, you can say that the universe is finite to the past. That has a very definite meaning that time-like geodesics have a finite.
But you might also think that what you need for something like statistical mechanics is a boundary, is a condition holding at a certain time, not necessarily the beginning of the universe. The past hypothesis.
Right. Yeah, that's fine.
You might stipulate that the past hypothesis that a certain amount of time ago the entropy was low. You might be very happy to evolve that out semi-infinitely in both directions from the past hypothesis. There's no necessary reason to associate the past hypothesis with the beginning of time or something like that.
Right. I didn't intend to say. This is just a question, sort of the standard question addressed by the singularity theorems.
Right.
Are there incomplete geodesics?
Right.
So, and I'm going to ask the question of whether all we can say is it's a boundary condition as opposed to a true initial state. So I thought the second was a clear way of saying it. So the FLRW models, of course, are highly symmetric, and so your suspicion is immediately that this might be a property that only holds for those models. But the singularity theorems generalize this result and show that it's actually quite generic in spacetimes that there will be incomplete curves. It's quite generic in spacetimes because of essentially two features. The first is that gravity is attractive, and so if you have positive energy density, that leads to convergence of nearby geodesic curves. If you have a geodesic congruence that's appropriately specified, you will have space-time curvature will lead to those collapsing or moving towards each other, and that will lead to the development of conjugate points, which you can think of as where two neighboring infinitesimally nearby geodesics cross. Now, the singularity theorems work by deriving a contradiction between that property of focusing and the claim that maximal curves will always be geodesics with no conjugate points. And so, in certain sorts of spacetimes, you can say that you can't have complete geodesics because they'd be incompatible with this focusing property. So, just to give you a sense of, so there's a whole number of different theorems, singularity theorems, starting in the 60s. I just wanted to give you a sense of the kind of conditions that need to be made. This is all in the context of classical general relativity that need to be made in order to prove these. And then I think we can say something a bit more specific about whether we'd expect these, what we'd expect these to apply for the early universe. So there's basically three types of conditions here. The first one is a claim about the curvature that congruence of curves will encounter. So the first requirement there, the Ricci tensor, if you hit it with a time-like or null vector, is always greater than or equal to 0. That follows from Einstein's field equations and the strong energy condition, which is a constraint on the type of matter and energy you have. So it rules out something that has negative energy density or substantial negative pressure. So that is the more precise way of saying that gravity is attractive and leads to this focusing of geodesics. The second condition there is just that they're, all time-like or null curves will hit some region of positive curvature, so that they aren't all going through a flat geometry. So those are called the generic conditions. A second condition is just a requirement that your space-time isn't causally bizarre and have closed time-like curves. And the third condition is a statement that is usually taken to be justified by cosmology. Namely, there is a point such that the expansion of a congruence of past directed null geodesics, if you think of going back in time from where we are, is negative. And so that's a claim about how the null curves emanating from a point behave as you track back into time. And as I said, there are different ways of proving the theorems where you have different conditions of these forms. This is one of the singularity theorems that has relatively weak conditions here. But note that it's a reductio proof, and all you get is the conclusion that there's at least one incomplete geodesic in the space-time. Right? So unlike the FLRW models where the symmetry allowed you to say something quite specific about the initial singularity in those models, here it doesn't actually say that much. It does say that there's an incomplete geodesic. And so I think it's appropriate to say that that's a singular space-time, and that's sort of the standard definition of what singular space-time is, that it has an incomplete geodesic. Now, we can then ask, well, how much have we built in? I mean, this is all proved within classical GR, and if we're asking about the early universe, we have an expectation that GR is going to break down at some point. So we can ask how these singularity theorems could break down as we extend past GR. So the first claim, let me focus on the first claim about curvature leading to focusing of geodesics, that actually has relatively weak dependence on Einstein's field equations. What I mean by that is just that even in some in a fairly wide class of modifications of the field equations, you'll still have that feature. But on the other hand, the energy conditions fail. So you've probably all heard this several times already, but dark energy or inflation, the scalar fields in the false vacuum state just directly violate the strong energy condition. And there are other situations where quantum fields violate the weak energy condition as well. So the energy conditions that you need to say that positive, or that the presence of matter leads to focusing, fail. The causal structure, that seems like a set of constraints that are more general than just classical general relativity, so that seems like that could extend past classical GR. And the assumption in the theorem that I quoted from Wald's book, that assumption about cosmology is actually quite modest. So if you look at the expansion of null geodesics from the present time, where that expansion becomes negative, which is all that that assumption requires, is actually well past decoupling. So it's more recent than decoupling. So that seems like something that is well justified within the domain in which we think relativity works. So what then can we say about extending these singularity theorems to cases that we're interested in the current context, where we have fields that violate the energy conditions and we're considering inflation? So I think Anthony might have already spoken about this last week. There's a theorem due to Bordi, Guth, and Volinkin from 2003, which isn't really a singularity theorem, but they proved a theorem in which you don't have to assume the energy conditions. So in that sense, you can try to avoid the problem with the classical singularity theorems because you know that the energy conditions are violated. And they showed that if the average expansion rate, so again, they defined a local expansion rate for a congruence of geodesics, and if the average expansion rate for that is always greater than some lower bound, then there's an upper bound on the integral of the expansion rate. And that implies that there's a past incomplete curve. The problem with this is that it doesn't imply anything as strong as, say, a curvature singularity, which is what you might think of as a singularity, such as in the FLRW models. And I think it's probably better just to say that what this establishes is that there's a boundary on the region that's covered by general relativity. So there are incomplete curves, but it's not clear that there's anything like a curvature blow-up that happens as you approach that boundary. So I think that, and this is in line with what Sean said yesterday, what we've established here isn't anything as strong as there's a singularity in the early universe. Rather, there's a boundary past which classical general relativity
I'm not sure I
Sorry.
even agree with that. I think
You can, yeah, sorry.
I think that the right way to say it really is to say that there's a boundary to the region that satisfies the conditions of the theorem.
Right, right.
And those conditions failing certainly does not mean that the space
The
time
general
is even,
relativity fails,
the
yeah.
general relativity fails or anything like
Right.
that in my opinion.
No, I think that's right, and I misspoke a moment ago, so I think it's a boundary even in a weaker sense. What you've just shown is that there are some geodesics that approach this bound, but that doesn't mean that the space-time can't be smooth through the boundary. Okay, so and I think part of the problem is that it's very difficult to prove something without assuming the energy conditions is nearly as strong as the classical singularity theorems. So if you're in a context where you don't want to make assumptions about the energy conditions, you can't show something nearly as strong as the result I cited earlier. Another question, so that's a way of reassessing the singularity theorems where you look at a specific aspect that fails, namely that you no longer assume the energy conditions. But there are also some discussions of quantum gravity effects that are, in some sense, might involve a deeper change in understanding of space-time as we approach a singularity. So, so these are all, I think, fairly controversial, but each of them suggests, in a different theory of quantum gravity, how things look differently in the neighborhood of singularity. So, Boyewald and Ashtekar have argued that you have a bound on curvature as the singularity is approached. It's bounded above, and that you actually have a dynamical evolution that extends through a classical singularity. In string theory, some singularities may be resolved by extra degrees of freedom. So again, that might allow you to evade the conclusion that you have a singularity. And finally, in the cyclic cosmologies pursued by Turok, Steinhardt, and others, there's a question about whether you can have a continuation through a singularity when you have a theory that's formulated in a higher dimensional space. So I think in all of these cases, the further theory beyond classical general relativity leads you to a quite different perspective on how to treat the singularity. Yes?
So just a short remark. So it's not necessarily cyclic cosmologies. The oldest versions is correct. These were in the brain pictures using at least 5 dimensions, but the newest pictures don't need 5 dimensions. So you can do cyclic cosmologies also within the 4-dimensional space-time. It's just these are the newest papers and the ones which are coming out.
Okay, so they do it.
It's not you can do it with non-union coupled gravity with 2 scalar fields.
And you still have a continuation through the singularity.
Yes,
in
that's the
some.
interesting thing is you have geodesical completeness. Geodesical completeness.
But now I'm confused. So the previous cyclic cosmology had 2 singularity issues or encounters or something. One was every time the brains came together.
Yes.
The other was by application of the Bordet-Blanken theorem that the overall setup was geodesically incomplete. So you're saying both of those are fixed by this,
So
or
the
first
one is the second one you mentioned is already fixed. Through 2 papers which were published a year ago, 2012 by Bars, Steinhardt, Turok, and Chen. These are the geodesically complete solutions. They have completed them analytically. And the second one is, I'm not sure if it's already published or they are just publishing it in the next weeks when they show that the first problem you mentioned they have for this. They do it. So paper came out on conformal symmetry 2 days ago, and this already implies higher parameters, 2 scalar fields that might solve the problem. So this is the
Okay. Well, that would be very interesting because they have to get around this.
This is a very interesting thing how they do it. It might be so. Sorry, I don't want to. Sorry.
Yeah, you can talk about this later.
So Sean, and then in the back, you had. Oh, I thought you had.
No,
Somebody else?
you very good.
Okay.
Yes, I just wanted to sort of highlight what Anthony has already noted. I mean, it's not as if adding quantum gravity effects is enough to evade the proper application of the Bordet-Blanken theorem. as Anthony hinted at, in the original 2003 paper, BTV applied their theorem to the cyclic cosmologies, at least the early papers, at least I'm thinking particularly the ones published in 2002. I haven't read the more recent ones that Anna was referring to. Also, they applied to higher dimensional theories, like Martin Bucher's in 2002. So I just want to make sure it's clear that, saying, oh, quantum gravity is going to rescue us, that's not a sure thing.
Right, and I think what I said about the cyclic cosmologies, even about the earlier cases, probably wasn't quite right. I think their claim is not that there's no singularity, it's rather that you can continue through the singularity in a sense which is kosher. And I think then the debate is partly about whether the claim of continuation through the singularity is actually kosher.
So the sense in which I've seen the theorems applied several times to the cyclic cosmologies and to the, like I said, one of the higher dimensional theories, is that there's the implication that the models can't be eternal toward the past, and that there is a boundary condition, and that the models are generally, at least null geodesically, incomplete. It seems like there are interpretive issues among various experts in the audience about how to understand all that, but I mean, that it's not eternal toward the past seems to me to be a sort of important implication for present purposes. I don't know.
Right, so again, I think the question is partly, there's two questions. One is it finite to the past or eternal to the past? Another way of rephrasing that is it geodesically incomplete? And also, if it is geodesically incomplete and there's some sort of boundary, how do you handle that boundary? And what I was suggesting is that I think the early papers on the cyclic cosmologies that I looked at, I haven't looked at the more recent treatments, the claim isn't that there's no boundaries, that you can actually have continuity conditions imposed on that boundary that are sensible so that you can have density perturbations that are formed in an earlier phase that then continue on and so forth.
Yeah,
So,
and I'm saying that the way that these theorems get applied, no, there's a sure boundary to the entire posited space-time, and that's because on the cyclic models, the Hubble constant or parameter is on average greater than 0 as you cycle through. So there's going to be a boundary to the entire ultra-large-scale structure. That's how I've seen it applied in some cases.
Sorry, not quite correct. I would totally agree with you. So there is a non-singular bounds theory and singular bounds theory both are. So the group does, some parts of the group who work on singular bounds theories, then go actually through a singularity and have geodesic completeness by going through the singularity. And others compute non-singular bounds if there is no singular. But cyclic cosmologies not necessarily imply no singularities. It's more about geodesic completeness and unitarity.
So I mean, I'm thinking of Malinkin Matheny 2013, Malinkin 2013 A and B. I mean, that's where I've seen it applied in the express way I'm suggesting. So I just, yeah.
Okay, thank you. So all I meant to highlight in this discussion is that our initial question, if we want to ask about extending the singularity theorems and whether we can say with any confidence, based on classical general relativity, that the universe is finite in the past, we have to address these three issues, I think in increasing order of difficulty. First, just the status of the energy conditions. That's the most conservative. You sort of imagine classical general relativity and you just put in a different type of matter and energy that violates the energy conditions and see what happens. Then there's the question, as we've seen, there's some interpretive difficulties associated with these more general singularity theorems, the Bordy-Guth-Malinkin results. And finally then, I think that the hardest question in relation to this is assessing quantum gravity effects at the Planck scale and seeing how those impact the idea that time is finite in the past. So again, I'm sort of overall agreement with Sean that there's a number of questions here which force us to look past classical general relativity, but I think you can actually see what ways in which general relativity might break down and try to assess the implications of those ways it could break down. So one other point I want to make fairly briefly is just to ask, if we had a singularity, what is so bad about that, or what would be objectionable about a singularity? So there's a lot of times in the physics literature, there's just a kind of abhorrence of singularities. And I think there's some questions about exactly what is so problematic about singularities that needs to be posed. So, for example, one worry might be that you have a failure of determinism associated with the singularity. The physics, breaks down. It doesn't actually allow you to determine how a state evolves or something of that sort. But that isn't going to be quite right, just because in some cases you have models that are singular that have a Cauchy surface. They have a well-posed initial value formulation, such as in the FLRW models. So it isn't all singularities that are going to pose a threat of this form. And of course, the Penrose's cosmic censorship proposal was partially motivated by the idea that there are some singularities that you might want to rule out, naked singularities, because they do pose a threat to determinism, but not all singularities will have that form. So it doesn't seem like you can just say we can't have a theory with singularities because of a failure of determinism. I also think it's hard to be careful about what we mean by the breakdown of general relativity. So often it's said that singularities show that general relativity is proving itself to be wrong or proving its incompleteness, something of that sort. That's partly difficult because singularities aren't localized regions within space-time. There's no region within a classical space-time where the singularity exists or where the curvature scalar blows up, or So it isn't as if there's a region within classical space-time where general relativity fails. It's rather that the singularity theorems indicate that you have to put a boundary on the space-time of certain sorts. And you could think of that then as indicating a boundary of the domain of applicability of general relativity. And so I think the response to singularities that I think is more reasonable is not that we can't have those in our theory, but rather that they do indicate a boundary of the domain of applicability, and that we would think, for example, that quantum effects would be important in strong curvature regimes, and so that where singularities occur, it's a natural place to look for new insights from combining general relativity with quantum theories.
Yeah, is there a distinction between saying that something indicates a boundary of the applicability of a certain theory, and saying this shows that the theory in question couldn't be a fundamental universal theory?
I didn't take myself to be saying that it couldn't be so the question, as I was posing it, is there a way in which general relativity shows that it's incomplete, or sort of demonstrates, here's the region where general relativity breaks down?
Well, you're right in saying it's not the case that it says here's the region in the sense of a spatial region.
Right, but there's a boundary.
It points to domains of applicability, which are in some sense less wide than we would want from the final theory, right?
Yeah.
So
it's in some sense indicating incompleteness,
right.
but I think in a much weaker sense than some of these arguments typically.
Sure.
Typically present.
What could have a singularity in fundamental theory? Maybe I'm misreading what you just said, but having a singularity doesn't seem like it seems like a fundamental theory can have singularities, and it could probably, I don't know what the problem is.
Well, so what I think my intuition was similar, that just saying that a theory has a singularity isn't itself an objection to the theory. I think that's what I took to be nature abhors a singularity. So somehow you think, well, if a theory has a singularity, then it must not be correct. I meant to be saying there's two types of arguments that I think often get run out as to why you think a theory with a singularity is problematic, and to be disagreeing with both.
I guess I didn't understand what David was saying. At the end there.
Oh, just
about singularities.
Say it again.
Well, what do you think singularity suggests in general relativity?
I wasn't propounding a view of my own. I was just trying to understand better what he was saying.
I think David was pushing me to say what the difference is between singularities indicate a breakdown of general relativity and singularities indicate a boundary of general applicability.
Okay.
So, this might come apart a bit in if you had a case where general relativity, classical general relativity predicted a singularity, but you had no reason to expect that quantum effects were present or that something would be important, then that would remove an additional reason that I was thinking of for saying that this is a domain of applicability. So then your question would be really, is it just the fact that there's a singularity that indicates that that sort of is a boundary of the domain of applicability? I think that's a good question. Yes?
Just kind of rephrasing that question, you could ask it by saying, if you find that your theory has a singularity, does that give you reason to believe that there's an even more fundamental, deeper theory that would make that singularity go away? And that's usually what people think of when they think of talking about quantum gravity, whether you go through the singularity or smoothing it out.
Yeah, no, I think that's a common argument, but I think there are reasons to think that quantum effects would have a particular impact on the singularity theorems and allow you to smooth out a singularity and so on. And then there's a different line of argument, which is you have to have a fundamental theory which gets rid of singularities. And the thing that I don't want to endorse is the latter, right? So I would say, yes, you have indications that classical general relativity is breaking down and you'd expect quantum effects to be important. To just say that you can't have a singularity in fundamental theory is not what I'm going to endorse.
Yeah, and just to finish, as far as I know, quantum mechanics doesn't have any kind of singularity of the same sort, which is why many people believe it's more fundamental than GR, and it's probably the more important of the two in terms of formulating quantum gravity.
Yeah, I don't know how. Yeah, so
people certainly use singularities as a motivation for it's an aesthetic criterion perhaps for what makes a theory more fundamental than another one.
Right. I mean, I would say classical general relativity isn't fundamental because it's classical. Forget about whether it has singularities. I mean, it's just a classical field theory. So, yeah.
Yeah. So, just check. I think from what you've been saying. But just to check, so this idea of singularity is an indication of the boundary of domain applicability is like quite a specific comment about singularities as they appear in GR, rather than singularities as they appear in
Yeah. And I mean, if I were to be more careful, I'd probably have to, I mean, singularities end up being a very hard thing. There's all kinds of different definitions that you can have of singularities. So I'd probably have to be more specific about which ones are actually a good indication of a boundary of domain of applicability. I mean, there's all kinds of bizarre behaviors that you can class as singular in some sense in general relativity. And I think probably only a few of those would qualify as indicating that you have a boundary of the domain of applicability. But let me move on here. So now I wanted to return then to some of the dialectic that Sean went through, which I'm cashing out as two different versions of a dynamical approach. The first one, in the early motivation for inflationary cosmology, what I'm calling old rhetoric here, you say that the advantage of inflation is that it washes away the dependence on initial conditions. And then there's a second version, which we saw yesterday and you've heard a lot about, which is that the multiverse might lead to sort of a equilibrium state, by which I mean a static distribution of bubble universes of certain types, and that you could then make predictions in that multiverse that would be independent of the starting point or initial nucleation event for that multiverse. And so I want to see, analyze the shift from the old rhetoric to the new rhetoric. And I'll say just for the sake of, so I'm going to be mentioning the other possible approach, namely that you have a postulate or constraint on initial state. As David mentioned, you don't have to think of the past hypothesis as constrained to the initial state, but I'm going to be bringing that up at various points. And I'm going to mention that there's a very different way of approaching these issues, which I won't discuss so I don't understand it well enough, which is theories of quantum cosmology, which propose a wave function of the universe or directly propose a constraint on the initial state. And so that's a very different way of handling an initial state. So I'll do this very quickly. The old rhetoric for inflation, due to the causal structure, namely the horizon problem or smoothness problem in the dynamics, the standard cosmological model apparently requires pre-established harmony in the sense of various different regions having similar temperatures. and a finely tuned initial value of lambda. As we saw, there's an implicit judgment about probabilities in saying that this is a finely tuned initial value of lambda, and depending on your choice of measure,
You're saying lambda, but you mean omega.
or sorry, yeah, you're right, in the value of omega. So there's an implicit choice of measure that was for a long time not really acknowledged, and so the standard treatments of the flatness problem didn't actually say what measure you're evaluating omega with respect to. So here's the picture of the horizon problem, as you've probably seen before. The points on on the surface of blast scattering that we can see, P and Q. Of course, the surface of blast scattering should be much, much closer to the singularity extrapolated from general relativity. But in any case, the points on those path light cones do not overlap. And so then it's a question as to why the conditions are so uniform or smooth between those points. And then the flatness problem is partly just a reflection on the dynamical behavior of the value of omega that's driven rapidly away from 1 with expansion. So again, I take those to be familiar by now. And inflation is meant to solve these because the horizon distance is stretched by a factor of e to the n for n and e foldings, and it also drives omega close to 1. And you then end up with a uniform flat patch as the generic post-inflationary state for sufficiently large n. So I don't mean to be endorsing this, as should be obvious, but this is the kind of standard old rhetoric that you still get a lot of times in motivating inflation. So now, what are the puzzles associated with this account, and why do we not want to endorse this? Well, as Sean mentioned, there's an argument made by Penrose very early on that seems to have been oddly ignored for quite some time, and that's that there's something quite puzzling about this case for inflation, namely that if you have a measure that's invariant during the inflationary stage. So, for example, the measure, the Gibbons-Hawking-Stewart measure that Sean talked about yesterday. If the measure is invariant under the dynamics, then the pre-inflationary state must be less probable than the post-inflationary state. So you can't have a generic output state. You actually have to have a more finely tuned initial state. And so all that we've done with inflation is replace the original fine-tuning that was seen as a problem in the standard cosmological model with fine-tuning of the state of the inflaton field. There's a lot of people who've discussed this. Penrose in 2004 has a nice formulation of it. Now, I should acknowledge, and there's a question which I haven't seen much discussed, but underlying this argument is the assumption that the evolution is unitary, so that you have this property of preserving the measure. And so there's an exchange between Kaufman, Linde, et al., and Hollins and Wall in 2002, where they explicitly denied that the evolution would be unitary. And so if you have a non-unitary evolution during the inflationary phase, then of course you can avoid this argument.
Kaufman denied it was unitary. Hollins and Wall said it was.
No, sorry, that's what I meant to say. So Kaufman et al. Said that it was non-unitary, and Hollins and Wall said that it was. That's right. So I just mentioned that as a loophole, but of course if you don't have unitary dynamics, then you don't have the problem that Penrose pointed to. But it seems that most people assume that this is unitary dynamics.
Can you say a little more about that? I mean, I've been given to understand that inflation, at least in various primitive versions of it, is just a solution to the Einstein equations. We've certainly got a Liouville theorem about that, no?
Yeah, you do. They just did a sloppy job and ignored some degrees of freedom and found that for the other degrees of freedom it was not unitary.
Yeah,
That's not good.
Has anybody else endorsed sort of non-unitarity for other? Yeah.
Good. Yeah, so there seems to be no reason at all to suspect
Yeah.
that it's not unitary.
It's just a macroscopic coarse grained proof.
But that happens a lot, Joe. Yeah.
Yeah, this may or may not be relevant, but when you're talking about whether or not the inflation actually makes you less probable or more probable.
Mhm.
Another thing that you might want to put on the table is the fact, or the claim rather, that inflation solves more than one problem.
Mm.
In addition to solving the horizon and flatness problem, it gets rid of monopoles,
Right.
and it also allegedly produces density fluctuations that we see in the Hilbert background.
Right. I was
So
gonna
you have
that
to
in
put
the
that
table.
probability into your statement of less probable, or maybe
Right.
not, I'm not sure, but I just want to put that thought on the table for you.
Yeah, I was going to come back to that in just a moment.
Okay.
I think there's a different way of motivating inflation where you don't rely on the claim about inflation as solving the fine-tuning problems, but rather motivate inflation because of what it does for an account structure formation. So, yes.
Yeah, but there's a sense in which sometimes when you solve one problem, you can create another. And that's not necessarily an argument against your particular solution. This is just following up on what you said, that you have to weigh all the new benefits of what you get versus the new problem. You have to decide, have you moved on to a series of better problems or not? And that's a difficult question to answer.
Right, so what I'm saying here is just that there's one aspect of the original rhetoric that motivated inflation, which I think is misleading. That doesn't mean there's no other case for inflation to be made. And I'm about to go on to say how you might make a case for inflation, which I don't think requires making these claims about solving fine-tuning problems or washing away dependence on initial conditions. So that's certainly the case. So let me just say, I think this is a version of the same argument, but if we imagine now trying to retrodict from what we think of as the present state, and we ask, what will the generic trajectories that got us to this state look like? Those will look nothing like our observed history, right? I mean, this is just the same point as Penrose made, slightly differently phrased. So rather than having the long evolution from the inflationary state till now, we'd expect to see growing inhomogeneities. You wouldn't expect everything to be synchronized just right to push the inflaton field back up its effective potential, and so on. And this is just like the sort of standard cases of looking at a glass of water with ice in it and asking what your physics would predict if you just take the present state. Should it predict a lower entropy state or going on a higher entropy? And this is the same point here. So of course, if we admit the past hypothesis as a constraint on the initial conditions of the inflaton field, you'd have to do some work to formulate that more precisely. You could get out of this objection. You'd be able to then say, well, conditionalized on the inflaton field being in a particular initial state, then the standard account of inflation goes forward. But this use of the past hypothesis seems to directly conflict with the kinds of case, the rhetoric that we have in favor of inflation. Now, I think there's a further question here, which is related to, so Sean yesterday was very careful to say what his dissatisfaction was with the initial conditions for inflation, that they were in some sense unnatural or small measure. He didn't go on and say they're improbable, right? I take it that so acknowledging Penrose's point forces you to say there is something special about the initial conditions that would lead to inflation in terms of the state of the inflaton field. And you might think that that then calls out for further, something further, namely, how do we get this set of initial conditions? And I think one of the things that's interesting is whether that is undermined by the use of the past hypothesis in this case. So in particular, if you're willing to say that we can postulate the past hypothesis as a claim about the initial conditions required for inflation, what further question are you left with regarding those the status of those initial states? So once you formulate the past hypothesis, you'll have a notion of probability that you apply. But what further notion of probability could you assign to those initial conditions? So this is where I expected everyone to erupt with questions.
I mean, this is just to amplify what you just said. There is some kind of, one plays a dialectical game of saying, okay, prima facie, this initial state looks highly improbable, and you posit a past hypothesis, blah, blah, blah. But, I mean, then a question arises, what kind of talk were you engaging in exactly in the first place when you characterized this as improbable? Improbable with respect to some probability distribution. Which probability distribution? The uniform one over the entire phase space. Where did you get the idea that that was the right probability distribution? Presumably from a priori principle of indifference kinds of arguments.
Right.
Are those arguments good? No. Okay. So what is the probability distribution? Well, presumably the one that empirically succeeds. Okay. If that's the case, is there any remaining sense in which those things can be characterized as improbable? No.
So I should say, just to be clear, you didn't say probable, right? So you said unnatural or small measure.
Yeah, and I think it is, it is an important distinction because it's the distinction between what you can do that works and what clues you should take from what the universe is telling you about how to do better. Because again, I'm just repeating myself, but we know that we don't have the final theory of cosmology. We know that just imposing a past hypothesis works and you can stop them, but maybe the fact that these initial conditions are very unnatural in this measure that dynamics gives us is a clue to constructing something closer to the final theory of physics and cosmology.
Right.
And maybe not, but that's what we have. You take the fingerprints we have, not the fingerprints we'd like to have.
Yes, in the back.
Okay, so I have a question actually, it's a follow-up from David. Even if we cannot ask or cannot carry something is probable or improbable, couldn't we still ask a different question that we have something to explain? Because if there are initial conditions, even if they are probable or not probable or whatever, we better don't say anything about their probability, but we still know that they need to be plugged into the theory. So wouldn't it be better not to do this but explain the conditions dynamically?
I mean, like Sean just said, if there's a way of making things hang together more prettily than we can now, nobody's going to be against that.
But then you don't need the probability.
That's great. But the way you were, that's right. But the way you were describing it seems to me make it much more stark than it actually is. That is, on the existence theories, the past hypothesis isn't something that you plug into the theory. It's one of the fundamental laws. Okay. Why would you? What's at stake in calling it a fundamental law? Well, on any sort of Jungian picture of what a law is, it's one of the things that's going to pop out in the fundamental law. It gives you, in a very concise way, extremely general information about how the world is. Okay. It's a law in exactly the same sense that the fundamental dynamical laws.
So
you can also ask a question. You could also get yourself in the mood to say, why should it have been exactly F equals MA? Why not F equals 5 MA? I mean, what are the chances that it would turn out to be exactly F equals MA? We need a deeper explanation of that. We get very curious about that and very nervous about that, blah, blah, blah. And maybe that is a good thing to get nervous about. If somehow you come up with a more elegant theory which starts with a simpler postulate than F equals MA, and F equals MA comes out of that, that's great, but it's certainly not necessary. It might be that F equals MA is law-like bedrock, and it might be that the past hypothesis is law-like bedrock, and it might not be.
But I meant the simpler thing.
Yeah.
So I'm not arguing about the laws, but as soon as we have numbers like constants, these are initial conditions. So I was talking about these guys, not about the form of those. I agree that this is a harder question.
But what David's saying is that...
For example, number, why do we have the value for lambda as it is? Why do we have the value of the constant, the 27 or 26 constants of the standard model? These are numbers which you plug into the theory. And when I met initial conditions, I thought maybe you can measure, maybe you can say,
okay. So, I mean, that's a little bit different than what we were talking about as initial conditions here, but I think the same kind of reasoning applies. It may be that there's more to say about those. If there's a more elegant way to knit them together, everybody's going to be very happy. It may be that they are sort of bedrock law-like statements. It's not clear to me how to decide in advance.
I'm happy with the physics which have 10 to 7 of these numbers.
No, if the question is, am I happier with a physics that has fewer? Of course.
Yes, so we have something to do, I guess.
Yes.
I'm not completely convinced that initial conditions are really necessary to articulate growth. I mean, suppose you had a steady state theory or the state space of theory has trajectories which are infinite to the past and future. Still, there's a question you can ask, well, why are we on the trajectory we're in fact on rather than another? And that seems structurally identical to the question, well, why did we start in this state rather than the other? Is there something particularly worrying about initial conditions which are unlikely on some measure rather than trajectories which are unlikely on some measure?
Right, I thought you were going to go, there's a slightly different way of formulating the question as well, which is even if you had an eternal universe, you might ask, why was this one actualized rather than something else?
Yeah, I don't see how that question is any different.
Yeah, no, I think that's the same question as, so,
Right.
if you think that there's, so I think here, let me put it very generally. Imagine that you had a view that the laws of physics should uniquely specify just the actual universe, right? And then you wouldn't have any contingencies left over. You wouldn't be able to say, it would just happen to be the case that we were in this universe rather than another one. If you had that view, then both you might have a universe in which all the possible cases are eternal, and if you had any contingency in choosing among those, you'd still find it problematic. Just as you would find the choice of an initial state problematic if you had a universe that was finite to the past. But I think the question is, why would you accept a view of laws of physics that was sort of meant to eliminate all contingencies and give you only one actual universe as the only sort of consistent realization of the laws? So I think there is a question that you can pose that will be puzzling regardless of whether the universe is finite to the mass and has some initial state or is infinite, as long as there's still this worry about contingency. Okay, so Fred asked a question earlier about whether you should accept inflation for other reasons. And this is actually, this is from Andrew Little and David Lith's book on inflation and structure formation. They make the point very early on that they think of, they review the kind of standard argument for inflation, and they say these problems related to initial conditions can no longer be regarded as the strongest motivation for inflationary cosmology, because it's not at all clear that they could ever be used to falsify inflation. So note that they're not rejecting this for quite the reasons I have related to the Penrose argument, but just that they think it doesn't have any empirical content. Then they go on to say, by contrast to inflation as a theory of initial conditions, the model of inflation as a possible origin of structure in the universe is a powerfully predictive one. Different inflation models typically lead to different predictions for observed structures. So on, inflation as the origin of structure formation is therefore very much a proper science of prediction and observation. So I think that this could give you a very different way of making the case for inflationary cosmology as something that, for the case that there's a stage of inflation in the universe, there are various law-like connections between the properties of the inflaton field and how it evolved, and density perturbations and other features of the early universe, the fact that it's free of monopoles, and so on. And you might just make the case that these connections give us reason to think that the properties of the inflaton field are overdetermined by what we measure. So by overdetermination here, I'm thinking of something like the case that Perrin made for atomism, right? Where you say, Perrin said there are 19 different phenomena which you can think of as measuring Avogadro's number. All kinds of different phenomena. And his case for atomism was, look, all of these lead to compatible determinations of the value of Avogadro's number. So that gave him very powerful evidence that it was in fact reasonable to think that there were atomic constituents of matter that were all characterized in which this number was a crucial property. And you might think similarly that you could think of the properties of the inflaton field as being revealed by various features of the early universe and try to use those to determine the underlying properties of the inflaton field. I think there are two challenges to this, just that you're not going to have a list with 19 that's quite as impressive as Quran. It's going to be harder to have independent measurements of this sort. And it's also not clear that you'll have the sort of degree of overdetermination of the details that Quran had. But I just suggest this is a very different way of making a case for inflation, that the features of the observable universe sort of fix the properties of the inflaton field that would have produced what we see. And note that this case doesn't directly appeal to washing away initial conditions or anything like that. Yes?
I think worth mentioning in this context is that until recently, the kinds of perturbations, structure formation, initial conditions that inflation predicted were ones that had all been used as toy models before inflation came along, right? Scale-free, adiabatic, blah, 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 blah. Inflation did make one additional it makes more than one additional prediction, but one that it made that seems to come true is that it's not precisely scale-free perturbation. There is a tilt. And it's still not like absolutely rock solidly established, because if you can wiggle out of it with new degrees of freedom or whatever, but if that continues to be true, I think that's actually a very important piece of evidence in favor of either inflation or something along those lines.
Right.
And it also rules out a lot of the possibilities because they get the wrong tilt.
Sure.
Yeah.
Sorry, you get the wrong idea.
Oh, not all, each different theory of inflation gives you a different value for the tilt.
Right.
So if you can actually measure the tilt, you can rule out some class of the theories, which is
Actually, as Matt Johnson explained in great detail in his lectures about exactly this last week, you don't just get the tilt, he showed the standard plot, which is the tilt that is n sub s, versus r, the ratio of tensor to scalar fluctuations. In other words, gravity waves. Right.
Yeah.
And this the combination that currently still allows a fair amount of parameter space, but is going to be tightened very significantly by the polarization data collected by Planck, which has not yet been included in the analysis, but will be by next year.
Right.
So, I mean,
yeah, I think the process.
The point is that just as Light and Little said, or Little and Light said, this is a highly predictive part of the theory and very testable, and incidentally also makes all kinds of predictions about the CMB itself, including the polarization, and which have been successfully confirmed. So this is what inflation's really about as far as real astronomers are concerned.
Right. And I think that when you look at the development of the field, the case where inflation was tested against competitors, like different versions of topological defect theory as an account of structure formation, it was the aspect of inflation that gives rise to structure formation that was really probed by all of the development of the background radiation observations that allowed you to rule out these topological defect approaches.
All causal explanations, that is essentially non-inflationary explanations, have been convincingly ruled out and were years ago.
Yeah, so I'm in agreement that that's the venue for testing the theory. And what I'm emphasizing here is if you motivate inflation along these lines, then the worries about the rhetoric regarding washing away initial conditions don't seem to be, we can set aside that rhetoric and make a case for inflation along these lines. Yes, Anna, and then
Just a simple question, you were just told that this is the way how to falsify some models. Do you think that the inflationary paradigm is falsifiable?
Yeah, so that's I think my impression is that there's people like Little take a sort of phenomenological approach, and you just say, here's a parameter space that we're going to carve out areas which work, and because there are so many different models of inflation with different motivations and different connections with ideas in fundamental physics, it's not clear that at any point you might sort of broaden that parameter space out again, given some weird model or something that changes the dynamics in such a way that you can still have inflation compatible with something. I think that there's got to be a sort of implicit assumption about what the reasonable inflationary models are. Once you have a sort of space of possible models of inflation, then you can say more precisely how the observations will allow you to carve out which of those are compatible or incompatible with the observations. So I think as long as there's sort of ongoing debates about what a reasonable model of inflation are, it will be difficult to sort of directly rule out the idea overall. But there are, as I was saying, the phenomenological approach, if you just think of inflation as a stage of accelerated expansion, there are some very general features that if you rule those out, then I think inflationary model building might look more strained.
Could you name some of these features?
I can name one. If you go back to 1993, there was a crisis in cosmology because the age of the universe wasn't working out right. And one of the solutions was to make an open universe where omega total is 0.2 or 0.3, I don't know what the number was. It's possible to make an inflationary model that ends up with omega of 0.2 today, but it's really contrived. So if we had measured omega to be 0.2, inflationary paradigms would not be as in good shape as they are. Instead, we now, since that time, measured omega to be 1 plus or minus whatever its current error level is. It goes down every year. So there was a way to falsify it. It's just that it did turn out to be false. Yeah. So that's an example of what.
I know a discussion, but thank you for mentioning this. I think something like this, I precisely asked the question looking at something like this is still possible, that we have the conditions which would rule out inflation still. Because that defines a theory, or that constitutes a theory being physical, that we can name the conditions which, the empirical conditions which would rule out the theory.
So do you mean rule out the idea of inflation overall? Well, I think, so there's a few things. If you,
It's extremely easy to specify many conditions that would have ruled
if you
inflation
saw
out.
overall angular, sort of
The problem
overall
is that
rotation,
those conditions haven't ever been satisfied by observations, but they certainly could have been. For example, if the CMB fluctuations had turned out to be very different from what they actually turned out to be. For example, if they'd looked like the predictions of any of the causal models,
right,
that would have ruled out inflation.
right, or overall rotation.
Answer the question.
That would be,
Trivial,
Like a preferred axis.
yeah.
for example, or many other such things. Sure, those would of course have ruled out inflation, but they haven't been observed.
Okay. Yeah, no, so I think there's a set of questions here about how what we've actually been able to measure and how strong the case can be made along these lines. But I mean, my impression is that the case along these lines is actually what's been so powerful in favor of inflation, even as there's this other case focusing on washing out initial conditions, which seems less important. Yes?
I think you can make a case that if the successor column for future experiments measure omega curvature to be non-zero and measure it to be 0.000001, you would be really strained in believing the standard paradigm.
No, not at all. In fact, that's the expectation of the standard paradigm.
No,
Exactly at that scale of 10 to the minus 5. That could just be, I mean, that's exactly what we expect.
Okay, so I guess what I was thinking is that to solve the flatness problem, if you think it's actually a problem, in the early universe it would have to be, flat to within, let's say, 50 decimal places, or something like that. But you're saying that in today's universe, it would only have to be flat to 5 decimal places.
There are super horizon sized perturbations, so you can't plan things beyond type of length.
Exactly, that's the point. As everyone who studies the field knows.
Okay, but let's say it was you measured it to be 0.001.
Oh, that would be bad.
That's what I was trying to say.
Yeah, but you actually gave the 10 to the minus 5 case, which you can't rule out, and in fact, it's exactly what you expect.
Yes, I expect too many decimal places, but you agree that measuring curvature that's greater than 10 to the minus 5 would strain inflation.
Yeah, you can easily make models that'll do that, but it would be not what we expect.
Well, certainly, but Anna's asking, just straightforwardly, name something that could falsify inflation.
Yeah, that's what it would be. Okay, so I want to come back to then, this is something that David's already mentioned, just a question, a more philosophical question. What's the status of the past hypothesis compared to other basic principles or assumptions in physical theory? So since this has already come up, I can be fairly quick, but there's a way of thinking of the distinction between laws versus initial conditions in which you think of the past hypothesis as clearly a statement about initial conditions, and so therefore distinct in kind from other fundamental laws. But on some philosophical accounts of laws, it isn't, the distinctions aren't drawn that way. And so just to flesh out this suggestion, so on the Miller-Ramsey-Lewis approach to laws of nature, you think of the laws as axioms that sort of best systemize some body of knowledge. So what does that mean? Axioms that best combine strength and simplicity. So by strength, and these are somewhat vague, but strength, you mean something like you can derive a lot of consequences from them. And by simplicity, well, you mean that you have a small number of them, and they're perhaps easily stated. And so, on this account, it's fairly natural to think that the past hypothesis could plausibly come out as a law, that it might be something that figures in this system as an axiom. Just 1 second. Yeah. And so the immediate thing I want to emphasize is that you could then say that the evidence for the past hypothesis might be more like the evidence for a law, and similar to the kind of explanatory questions you might ask about the past hypothesis would be analogous to the explanatory questions you'd ask about laws, rather than treating them as different. That the initial, if you think of it as initial condition, there might be some sorts of explanatory questions that seem pressing. If you accept this account of laws, the landscape has shifted, and you should think of the question about the past hypothesis as similar to, as David was saying, why do we have these laws if you end up classifying it as a law? Luke?
Sorry, just trying to understand this approach to laws. Maximizing strength, that seems to be sort of relative to...
maximizing strength and simplicity, the combination of the two.
But that specific requirement, that seems to be relative to what your experimenters can do. So string theory, you can derive a lot of things from it, but you have no idea whether that's a strength or a weakness. Does that mean maximizes the number of derived and reasonably testable or potentially testable?
No. The fairy tale you're imagining here is you take it that the totality of the facts. You have a God's eye view of the world, okay? The totality of the particular facts is available, okay? And the things that count as laws are the things that are the most efficient and most powerful at summarizing the totality of facts.
Good. Yeah, so you have a Humean picture where the statement of the facts themselves don't involve laws or sort of law-like things. You just have a list of all the occurrent facts.
Yeah.
That's
all of them, whether we could measure them or not.
Yeah, and that's the deductive system, and you're trying to say, what can I assume as basic principles that would allow me to derive all of those, or as much of those as I can, without compromising and adding a bunch of, compromising simplicity by adding a ton of very specific pointing to it. So, again, this is, if you have this attitude towards laws and accept this philosophical account of laws, then I think the kinds of questions you'd ask about the past hypothesis are quite different. You ask about evidence for the past hypothesis as the same form as evidence for laws, and similarly, the explanatory questions will have a similar character. Okay, so that was one aside. I now want to come back to the, I guess this was the next step in Sean's dialectic yesterday, where we shift from the old rhetoric in favor of inflation to discussions of eternal inflation. So, so we have, rather than the idea that inflation washes away initial conditions, we have an argument that inflation is generically eternal in some appropriate sense, and that it leads to a multiverse from initial fluctuations. So in some sense, and this is I think what Sean was advocating, that we're going to replace the question regarding the unnaturalness of the initial conditions that was the old motivation for inflation with the question like, what does a typical observer in this multiverse see? And so, I just want to note something. I like this line from Sean's paper with Chen. So, in terms of what's required for an account of this initial fluctuation, they do a calculation of the probability that the inflaton field fluctuates up from a de Sitter vacuum to an appropriate initial state for eternal inflation. That's given by the number here, and they noted a footnote that this may be the smallest positive number in the history of physics. So we're gonna calculate, and I don't know any counterexamples to that. That's
Sadly, I think that this calculation was wrong, the number's actually bigger than that, so I don't think it is the smallest number.
But it might still be the smallest. I mean,
That
how
might
much
be,
bigger?
yeah, I might be wrong, but still the smallest number that I dared to write down.
So the point that I want to emphasize is that the power of the eternal inflation idea is that if you have an de Sitter vacuum state that's eternal that's sitting there, all you need is a non-zero number here, right, for an initial fluctuation to start, and then to have the eternal inflation picture kick in. Now, I want to focus on, so this is more reflections of my puzzlement about the sense in which the question we started with about the unnaturalness of initial conditions is really refined by shifting to eternal inflation. So there might be a few motivations for this transition to posing the question in this different way. So first of all, I think there's a shift in our understanding of the equilibrium state for quantum gravity. As Sean argued, that we have a way of associating entropy with different vacuum states that leads us to think that the de Sitter solution will be, that we shouldn't think of it as just picking solutions from the classical phase space of general relativity, but that we assign entropy to those, and then we have an understanding of the equilibrium state. Also, then we have particular accounts of how you generate a bubble nucleating in an appropriate phase and starting. What I sort of missed yesterday in the dialectic was why these are really answers to the questions we had posed about the initial conditions for inflation. So these are questions about what the status of the past hypothesis is in this picture, and does granting the past hypothesis in an earlier step of the argument undermine the need to propose eternal inflation? So I feel like this might be where you say it's a clue to further physics, as you said earlier, or...
I'm not sure what you mean by granting the past hypothesis. I mean, if you grant the correct past hypothesis, well, there is a past hypothesis you could grant, which would completely remove the need for inflation to be anything at all. So I think that the whole program is based on the idea of explaining the past hypothesis through dynamics, and the slightly ill-posed presumption at that stage of the dialectic is there's some wave function for the universe, many things could happen, let's focus on the thing that happens that begins inflation, and then you get an infinite number of observers who see proper Big Bang cosmology.
So sorry, that was ill-posed? That was...
The quantum initial conditions are ill-posed because we don't have the theory of quantum gravity, we don't know what the wave function of the universe is, but the argument is that there's a robust prediction that as long as there's some chance that inflation starts, it continues forever and makes an infinite number of observers. And again, that's just my formulation of that step in the argument, not my belief.
Right. Casey,
yeah, so here's just a general question. Why are dynamical explanations better than explanations that are on initial conditions?
Yeah, I think that, and specifically in this context, let's say you grant the dynamical explanation of eternal inflation, what do you get that you didn't already have by granting the past hypothesis? Or do you get something further by having this dynamical picture of the origin of the initial conditions?
One thing you could say is that dynamical explanations are necessarily better, but it's an alternative, and we should explore those options and see if we come up with something better.
I think it's obviously it's potentially a simpler, more, you get more for less.
Yeah.
You always have dynamics. You don't always necessarily have conditionalizations on initial conditions. So if you can get
it's
both
condition, right?
from...
Among the possible trajectories, like the question Alex asked,
But if
you're doing physics unless we have a space of possibilities.
That's right, but if every possibility makes the same prediction, then you don't need it.
No, it's not going to be that every possibility makes the same prediction. It's going to be that you have a measure over the possibilities that looks nice to you,
That's right.
according to which most of them make the same prediction.
Yes.
So it's never going to be all dynamics. It's going to be dynamics plus a measure at the very least. The question is there a hope of, as it were, producing a feeling that the measure fits with the dynamics better than in the cases we have worked out already. Does that seem right?
I think so. And in fact, I would predict that if there were a theory of cosmology with that property, that there were some dynamics and there was sort of the obvious dumb measure to choose, and that obvious dumb measure, you predicted everything and it worked, everyone would believe that was a
Right. Right.
So Andrew, and then
So you could ask the question of where do you want to put the past hypothesis? As we were discussing a little yesterday, you could place it, after nucleosynthesis happened, and then just posit, the light elements form. But by let's say placing it at the standard Big Bang, you then get a little bit of a more explanation. You have a story which tells you dynamically how the light elements form. You can keep playing that game and push the past hypothesis back as far as you have to and use it as a last resort. And then if you use it for the initial conditions for eternal inflation, then like Sean said, you get something, something that's quite simple as a starting point, and you get a lot more. But also, if there actually is this ensemble in the multiverse that really exists, you can make drastically incorrect predictions about what we should expect to observe if we ignore it. And we still have to solve the measure problem, but that we could end up making better predictions about what we should see in the world by including this extra stuff.
right, yeah, that's ultimately the hope. I'll talk a little bit more about getting predictions out of this picture in a moment. Anna?
So it's just a short remark because I have sometimes the impression I'm missing something, if you can tell me what. I thought that I would definitely choose something which explains, so if we have a dynamical explanation, we have an explanation. If we just assume initial condition, there's a real huge difference that we have no explanation. So I think the difference is, or how I see it, and please correct me if I miss something, that in the one hand, we do what physics is supposed to do. We are looking for explanation for something which is physical. And on the other hand, we just express that we need to assume we don't know anything about it. So that's because the original question was why to prefer dynamic explanation to a...
But the real challenge here, the real challenge is that if you have time reversal invariant dynamics, and what you're trying to explain is irreversible behavior, how are you going to get that just out of the dynamics?
But I think you can make it more general than that. Yeah, I think you are missing something.
Okay.
Look, there's take any fundamental physics which has the following property. The macroscopic objects of our everyday experience, are the upshots of large numbers of behaviors of very large numbers of microscopic degrees of freedom. In any theory like that, the dynamics is always going to allow it to be the case that, for example, that is, there's going to be a solution to the dynamical equations of motion, according to which the moon abruptly takes a right turn, because it's fired out one subatomic particle at extremely high velocity and with extremely high momentum in the other direction, and the moon suddenly takes a right turn, This is presumably going to be a property of solutions to any imaginable fundamental dynamical theory, which has the feature that, like I said, the behaviors of macroscopic objects are the upshots of the behaviors of huge numbers of microscopic degrees of freedom. There are always going to be ways of arranging, there are always going to be points in the phase space of the microscopic degrees of freedom that act crazy, This is going to be a feature of any microscopic dynamic, which has the general properties I was talking about. So in addition to the dynamics, you're always going to need some excuse for neglecting the crazy ones. You're always going to need some way of assuring yourself that you don't have to worry that the exact microscopic conditions are one of the crazy ones that are going to put you on a solution to the microscopic equations of motion, where the moon suddenly takes a left turn. Hold on 1 second. Or where an elephant suddenly appears in this room, or something like that. So in addition to the dynamics, there's always going to need to be something that amounts to a measure over initial conditions or a measure over trajectories or something like that. And to the extent that our expectations about ice melting and thermodynamics and macroscopic behavior and so on and so forth are even remotely law-like, those excuses for neglecting the crazy initial conditions are going to have the status of laws as well.
How can you be sure, why is it to assume that this excuse cannot be given us by the same theory?
You mean by the dynamic? I don't understand. If the structure of the theory is, here are the dynamics, the trajectories the dynamics allows are these. If the dynamics allows any crazy trajectories at all, then you're going to need something over and above the dynamics that amounts to an excuse for not worrying about them. I'm taking the dynamics to be just something that differentiates physically possible trajectories from physically impossible trajectories. That's what all the dynamical theories we've ever had do, okay? And our experience is that in all cases where the kinds of macroscopic behaviors that we encounter in our everyday lives are the upshots of the behaviors of fantastic numbers of microscopic degrees of freedom, then there are always going to be among the possible trajectories crazy ones. The dynamics, by definition, can't do anything to reassure you about those. You need a measure. Now, it may be, as Sean is hoping and so on, and as everybody would hope, that there are certain measures that fit together with the dynamics nicely or something like that, but there's always going to have to be something over and above the mere differentiation between those trajectories that are dynamically possible and those that aren't. You need some measure over them in order to neglect these crazy ones, in order to get any predictions out of the theory at all.
But, sorry, just one more thing, and I stopped there because, but how can you, so you only assume one dynamics and then leave an excuse. Why we cannot have a theory which is one dynamics about trajectories and one other dynamics about conditions we need to assume? For example, dynamically produced initial conditions taken up. I mean, okay, I cannot take for example, cycling or in the multiverse or whatever, that there is some attractor behavior which describes which kind of universe is
okay. If most of the dynamic, I mean, that might ultimately contribute to making one measure more reasonable than another. If there are attractors, I've never seen an attractor. There are attractors that sort of drag trajectories towards regions of phase space. Usually, the perverse trajectories are sprinkled throughout the entirety of the phase space, and you're not going to avoid them just by getting sucked into a certain region. But maybe there could be extreme versions of that.
Sorry, I shouldn't make promises. That was my last question. But that is, for example, it doesn't work because it produces an empty universe, but if you want to explain the cosmological constant, take the Bousso-Koczynski, it has problems. But I just want to give an example. Take the Bousso-Koczynski potential, and it can at least explain how the value of the cosmological constant could evolve.
Oh yeah, but this potential is an effective.
It's a dashboard, yes.
It's very.
Here's a pattern. It's a pattern for dynamical explanation.
Here's a claim I'll put on the table, and the interest of such claims is to falsify. Okay, but here's a claim I'll put on the table. It's really, really hard to imagine a genuinely fundamental theory, okay, where, like I said, the behaviors of familiar macroscopic objects are the upshots of the behaviors of fantastically large numbers of microscopic degrees of freedom. Here's a claim, like I say, a claim that's an invitation to be falsified. It's hard to imagine a genuinely fundamental microscopic theory that has that structure where there aren't going to be perverse available trajectories that you then need to rule out by adding a measure over the set of them. If that's false, that's really interesting. And that would be a really, really interesting theory. I'm sorry for this.
Oh, no.
Sorry.
Okay, so, let's see where. So, I wanted to come now to the question. This is came up earlier. Well, one consequence of buying the eternal inflation picture might be that you get predictions that go beyond what you would have gotten just by granting the past hypothesis in one form. And this is something that other people have spoken about with more insight and authority than I have, but the problem, and Sean mentioned this as the final step, I guess, of the skeptic's reply, which is, well, you've produced an infinite multiverse now. How do you get predictions out of that? And you have people saying, well, anything that can happen will happen. It seems like it's a little too promiscuous to really have some clear predictions that you can have. So, and Sean discussed the measure problem, and I think you probably heard about that earlier. I want to ask a few questions, some things that I find puzzling, even if you grant that you've come across a measure for the multiverse, even if you grant that you have a measure that somehow theoretically singled out and also regularizes the infinities. I think there's a further question about the reasoning that's involved in using that measure to make predictions. Again, if we think now that the way of thinking of eternal inflation is to ask what predictions does it make for a typical observer. So the first thing I want to focus on is this question of the notion of typicality, and then also just a question about how to carry out anthropic reasoning and some reasons why it seems like it's actually going to be quite challenging to do so. So again, this is returning to something that was discussed last week, but the doomsday argument I've taken as an illustration of the problems with using typicality reasoning. So if you evaluate the prediction of the total number of humans based on, say, an individual's birth rank, where that's just the number you are in the order, and we assume that n is greater than r. If we assume that we're typical, we'll apply the principle of indifference and just say the probability of us having a particular rank is just going to be 1 over that total number of humans. And then we assign our other probabilities as given here. These are, again, following Gott's analysis, but these are the other inputs into Bayes' theorem. And then when you apply Bayes' theorem, it's just straightforward. You get the probability of your birth rank, the probability of the number of humans given your birth rank is given by r over n squared. And this leads to, you can do a fairly quick calculation to show that this will favor a small number of n. So n will be within some factor, so it will be, this should be less than 20r. So the probability of n less than 20r should be less than 5%. Or no, sorry, the way I put it is right. Probability that's greater than 20r is less than 5%. So it's a very small probability that there's a lot more humans than your birth rank. And of course, the assumption of typicality comes in here, motivating this first probability. The probability of your birth rank given the number n as being 1 over n. So, so I think that the problem with this argument is that you learn far too much. And so you learn something about the future of the human race based just on a simple application of Bayes' theorem. And so that strikes me as an indication that you've packed too much in with the way you're assigning probabilities, the way you're using probabilities in this reasoning. So I think the question that this poses is, how do we want to describe real ignorance when we're reasoning and using and applying probabilities? So there's a few things to mention about how you might do this rather than just assigning a probability distribution as we saw in the previous slide. So John Norton has a paper addressing this in which he argues, I think correctly, that just assigning a uniform probability distribution doesn't really represent ignorance or neutral evidence, because the probabilities contain, that probability distribution has more information in it than you would want to assign if you were truly ignorant. And so John advocates an alternative inductive logic where you just assign something which is indifference to the cases where you are really ignorant. I think there's, and he actually also criticizes Bayesian approaches because they have people assign probability distributions over their beliefs. I think there's a way of doing this without abandoning Bayesianism. and this is due to following some work by Jim Joyce and other people in the statistics literature. And then Jan Benetrude-Pan has written a paper on this recently, saying that you can model in a Bayesian approach imprecise group probabilities by treating agents as having a set of probability distributions rather than a single probability distribution of their beliefs. And then the things on which they're committal are ones that are common to this set of probability distributions, but things of which you're truly ignorant are ones on which those probability distributions vary. And that captures something like what Norton wants to do, which is to avoid the conclusion of the doomsday argument, because the information that you're putting is not nearly as committal as the prior probability distribution that we motivated by indifference principle reasoning on the previous slide. Yes?
This is just to amplify this remark. I didn't know about this recent stuff that you just mentioned, but it sounds really interesting. But yeah, just to amplify what you said, there's an argument, I guess, going back to Laplace, okay, where he says, look, if the situation may, for all you know, be A, B, or C, and you have no clue which of those it is, there's only one thing you can do with your probability assignments that respects the symmetries of your epistemic situation, which is to assign a third, a third, a third. And it's just a logical mistake there. There's, like I was saying, you weren't here in the first week, but like I was saying in the first week, there's another thing you can do which respects the epistemic symmetries of your situation, which is to say, which part of I have no clue do you not understand, okay? I have no clue. I don't have any way of assigning probabilities over these. I have no clue. This also respects the symmetries of your epistemic situation.
Right, terrific. So Andrew and then Sean and then.
So I think you can also get out of the doomsday argument if it turns out there's a different number of observers in the reference class. Then the typicality, it's harder to say whether you can be toward the beginning or the end, for example.
Then you have like an improper probability distribution you're assigning.
Sure, that's one thing. But the second thing is
But you wouldn't evade the standard argument for finite end.
Say again?
You wouldn't evade the standard argument for finite end.
Probably not.
Yeah.
But I think you're absolutely hitting it on the head with the idea that the uniform prior is actually extremely informative in this case. So, and I can certainly ask Jan more offline, but is there a sense in which this approach is like assigning a uniform measure over probability distributions?
I think maybe you should ask Jan about this in more detail. I don't think you have to assume that the sets of creedal states that you're sort of assigning a collection of, call them creedal states, that's just assignments of a particular probability distribution to an agent, and then you're saying that in that collection there might be some things that all the probability distributions agree on, but I don't think you need to say that there's a uniform mixture of those sets for a given agent. You probably have to make some assumptions about that, but I think you'll have to ask Jan. And sorry, Sean, were you in the queue? And then okay, so Sean, and then is it Alistair? And then Luke. Okay.
Okay, so two things, hopefully quick. One is that in these cosmological scenarios that are big enough so that you get situations where precisely the same macroscopic data appears many times, this room appears many times, I think that you have to have, well, the choices are basically like David said, either have some procedure for assigning credences to the different ones, which is probably going to amount to giving them equal weight, or just say that theory makes no predictions about which one you are. And I don't think that there's any reason to be I don't think there's any reason why you should say the second thing. I think the first thing is perfectly okay and is necessary. But it only applies in that robust way to these situations where the macroscopic realizations are truly identical, indistinguishable, or within some epsilon of each other. And so the other thing is, in the doomsday argument, that's completely not the case, right? You're comparing very, very different people. Mm-hmm. And the idea that you should consider yourself typical among all human beings seems just obviously wrong, in the sense that we are not typical within people of the last 1,000 years. Why would we be typical among all human beings? maybe that would have some justification if human civilization had reached some sort of equilibrium, where over the past 10,000 years, people were more or less finding themselves in similar situations. But that's clearly not true now, that our situations are changing very rapidly, so why in the world would we assume that we're typical of that ensemble?
Yeah, so I'm really having a hard time sort of combining what you're saying about typicality here with your assertions about the duplicate case. I recognize that you're saying that there's reference classes that are different, but I meant to think of this as a very specific, simple case where an assumption of typicality, again, you're not asking about properties about your income level, your overall health. You're just asking how many humans are likely to follow. And so I think you could make the case that for this argument, the other aspects in which you differ from all other humans are not relevant. And so this is, on the part of the advocates of the argument, I think they'd say something in that form. I'm just arguing that the assumption of typicality itself, as displayed in a simple case, seems to pack in far too much information.
Yeah, and that's why I totally agree on that.
Right.
So
okay.
I
So you're thinking that
there isn't
a similar problem that arises in the duplicate?
Yeah, there's a real problem about in which class we are allowed to think of ourselves as typical. And I would say on the one hand, if the reference class is people with precisely the same macroscopic data, then we have to. If the reference class is much broader than that, then we can't. And finding exactly where to do it is a hard problem.
Ah, I see.
So just a quick follow-up on that first. I think what we're going to do with the doomsday argument is kind of set aside that extra information you have about yourself that distinguishes you from people 1,000 years ago, and then you have a doomsday effect. Then you can add back in that extra information, and that will shift you around, but you'll still have the doomsday effect kind of in the background, having affected the priors, and those will be kind of traces of it in your current predictive function. But I wanted to ask about the imprecise probabilities, because I'm not seeing how that's going to help with doomsday arguments at all. If you've got a set of predictive functions, and each one of those predictive functions in the set is getting doomsday shifted, then the whole set is going to get doomsday shifted as well. You can see how Norton's approach would help, because it just kind of, you can't assign credences to certain things at all, and that's kind of like a blocking move altogether. But the imprecise probability function approach is generally more interesting, but it's more.
Yeah, no, I don't think it's the case that they'll all get shifted by the same amount and that you'll still get the conclusion. But I think I should move on. So sorry, and Jan is here, so you can maybe ask him about that. I'm setting you up for all kinds of hard questions. But if you were
Slightly a question to you and slightly, the question is, when do I say there's three things, I don't know, probability a third, and when do I say that there's three things, I don't have a clue, so I don't have a clue?
Well,
I mean, according to, in Bayes' theorem, you update your probabilities once you start learning about things.
right.
But if the first thing you do is to say that there's the prior and it's, I don't know, then I'm going to use the mathematical equation. Anything times I don't know is I don't know.
Right.
Right, so then you can never update. Right, so you've got to do
That's what
something.
Norton
No,
does,
no, no,
basically.
I mean, this was supposed to be, this was, what I was presenting is supposed to be part of an argument, I guess, that it's not right to think about statistical mechanical probabilities as somehow following from or being a mathematical translation of our ignorance, okay? The reason we trust statistical mechanical probabilities is similar to the reason we trust any other law-like claims about the world. Empirical reasons. It's empirical success at predicting things, okay? That's what's going on. And it is the case that if you take this kind of empirical attitude towards fixing probabilities, which seems to me to be the right thing to do, it does make the whole business of self-locating probabilities much more puzzling. Okay? Self-locating probabilities are going to have to come from some kind of a priori argument. And I tend to be very deeply distrustful of a priori arguments. So vis-a-vis the probabilities we use in statistical mechanics, okay, what's the likelihood that this gas is in one of the microstates that's gonna make it expand and fill the box. There was an attempt early on in statistical mechanics to borrow things from the principle of indifference and so on and so forth, and that looked cool because it looked like it was going to give you something like this. And maybe this is related to what Andy was saying earlier, I'm not sure. It looked like if the probabilities were a priori, then really you were deriving thermodynamics just from the microscopic dynamical laws. Because everything else you needed, namely the measure, was a priori somehow. That seems to me radically false, okay? That's not what's going on. There are many probability measures that are compatible with the dynamics. There are an infinite number of probability measures which are compatible with dynamics. And the one you get just from the principle of indifference turns out to be radically wrong if you evolve it into the past. It does a good job toward the future. It does a very bad job toward the past. So you do the reasonable thing. You say, oh, excuse me, I was wrong. The empirical content of my theory is not just the dynamics. It's the dynamics plus the measure, okay? Those two combine to give me empirical predictions. With only the dynamics, I get no empirical predictions of any interest at all. I don't get the prediction that the moon isn't suddenly going to turn right or something like that. And so both of these are fundamental empirical components of my theory, and my reasons for believing them are empirical reasons. And that's exactly what puzzles me about self-locating probabilities, because you're not going to be able to, those seem to need to be a priori somehow. I'm very deeply distrustful of a priori components in our theory.
Yeah, I mean, I think the picture of being outside the universe and having an ensemble of physical systems that are all duplicates of each other,
Right.
and asking which of
Which
those
one
am
am
I?
Right.
The question of where do you assign probabilities?
This is very, very confusing to me. Yeah, very confusing.
David, can I ask you a follow-up with Anderson question? You say we can justify or measure empirically, right?
Yeah.
Okay, but for this you need to assume that your theory, which gives you the dynamics, is right or correct, right?
Well, no. What you do, as with all physical theories, is what you take to be empirically well confirmed or empirically disconfirmed is some combination of a dynamics and a measure. They come together.
But
You don't get one first and then
how
get
do you justify that you measure empirically if you need the measure to justify your dynamics, or that?
This is like saying in any theory where I have more than one fundamental physical law, how do I justify them together? I note that the package makes good empirical predictions. I can consider other packages. I can compare them for how good their empirical predictions are. I can do Bayesian updating on these packages, and eventually I converge on a package that's good, that's empirically good.
Don't I try with different dynamics to separate them, to test them?
You can do that too, but that's Bayesian update. That's another package.
But then I can do them separate, so I try.
Okay,
Sorry. Sorry. It's.
I'll make one final point, and then we can take a break for lunch. So I want to say, so there's, as I was saying, I think there's issues that are independent of the question of the measure for eternal inflation that are problematic. The first was an assumption of typicality, and the second is related to what I'm going to call anthropic reasoning, which is how is it that you take account of selection effects and make predictions in this sort of context. So, and this is really drawing on Anthony's work, and I think he discussed this in a lot more detail last week. But so if we consider some parameter and we have observational bounds on it, so let's imagine that we have some region of the multiverse that satisfies those bounds. And I'll just assume that we have a measure that regulates infinities and does all these other wonderful things for us. We also have to include some information about the anthropic subset, whether it's people with exactly our macroscopic data or observers or however we want to define that subset. Imagine that we say that there's a set of parameter values that are compatible with being members of that subset. Then if we assume typicality, we would say that the probability of getting the value that we observe or something compatible with what we observe is just the measure of that subset in which that parameter value holds over the anthropic subset, right? Something like this is what I'm taking to be the characteristic of anthropic reasoning. Now, one thing to note immediately is that if you go this route, you don't punish a theory for having predicted a vast number of pocket universes that don't have observers or don't have observers like us, or have you specified your initial class. So even though it might predict a number of those, you're only really focused on the anthropic subset. The problem is, how do we delimit that subset in such a way that we can make this prediction? And so this reflects as well on what Fred was saying about how you can have different regions of parameter space in which you might have something quite odd leading to the possibility of life in a region that you hadn't considered because it's far away from the sort of parameters we consider. And Anthony has a model of a cold Big Bang that does the same sort of thing, where it shows that there might be regions in parameter space that would fall within this subset of being compatible with life. So there's this issue then of how do we delimit the subset, given that we're supposedly making predictions in which we have to delimit the subset in order to know how to make the predictions. And I think that's actually a really hard question if you take this line of reasoning seriously. And then there's other issues, such as just the question of choosing which way of delimiting the subset you're interested in. I think Sean was just suggesting that if you go all the way to exact same data, then you can solve that reference class problem. But then you also, I think, still have this problem of determining how large that subset is in order to make predictions. So I think I'll close on that note. If there are any questions, we can discuss this final point. You'll be happy to know that I'm not going to talk about Boltzmann brains, which was the last topic I had in my slides. So thank you. I really wasn't going to talk about Boltzmann brains, sorry. Yes?
Could we not just make the specification of the anthropic subset, or whatever you want to call it, just consider those to be postulates of the theory, right? And then the simpler they are, the better, right? So if you have a postulate in there that's, we look around and see stars, that's pretty simple. But if you have to put in like loads of stuff about what we observe before you get any predictions, then it just means your theory's got a lot of postulates, and we use the normal theoretical grounds for saying something to do.
I'm not really sure. So the question I had was rather not, so let's assume that we have a relatively clear designation of what we want the subset to be. Then the question for me is, what regions of parameter space will fall within that subset, or what regions of the multiverse will actually be counted when we're looking around to see how many of those multiverses have the right parameter value, or how many of those subsets in the multiverse have the parameter values that we observe, right? So the worry is that you might think, okay, well, we've looked at parameters close to our universe, and we've determined that if we vary in this way, we don't get life, or if we vary in this way, we don't get life. So then we have this view of what the subset is going to be that's fairly narrow. But then you look at a completely different part of parameter space, and you discover, hey, there's this completely different way of making stars work. Perhaps that would lead to life. Then you have a different part of the parameter space in which you have a non-zero probability of observers, or life, let's say we're conditionalizing on life. And then the fact that that is true should change your predictions, because now the denominator has a different value. I don't know how it's going to change your predictions, but you know, if you're taking this seriously as a way of extracting predictive content from your theory, you know, you're going to have to be worried about how it is that you assess what regions of parameter space are compatible with life.
Sure, but this just again sounds like a problem that you have in any theory of some theories. It's really hard to get from what you're considering to be the postulates to what you're considering to be the predictions. Some theories, it's more tractable. And we just use our usual judgments to, you know, focus in on the more tractable ones. Or I just don't see how any of this is any different to the usual kind of judgments that we have to make when comparing standards to fixed, right? you could always have a problem that a scientific theory, looks attractive in some sense, but when you actually try and get predictions from it, it just turns out to be really hard, and someone comes along and points out you've forgotten something. And
I think there's a lot that you could, there are a lot of different ways in which extracting predictions can be hard, and I do think that this is fairly distinctive for the case of the multiverse. So I'm not saying that it's always easy to extract predictions or anything like that, but I think this particular question arises from the fact that you're defining the probabilities of observing certain parameter values based on their occurrences in a multiverse. And maybe there are similar situations in some way, but it seems distinctive from other cases of difficulties in extracting predictions. So,
Let's say you're conditioning on the existence of stars or galaxies as a proxy for observers. Then this will force us to learn about all the different ways that the universe can make stars or can make galaxies, and that's very different than the kinds of predictions I think that we're normally thinking about, like let's say trying to start with the fundamental constants of nature and then extract predictions from quantum mechanics or something like that.
yes.
This is about eternal inflation, so if we say. So you're following children saying there's an advantage to the eternal inflation picture, which is no matter how small the probability for inflation to get going at any stage, it will at some stage. And I just wanted to ask what you thought there was a kind of similar advantage to a picture where you have just kind of single shot inflation, combine that with a many worlds interpretation of quantum mechanics, because you're still going to get in some branch inflation going as long as there's a non-zero probability of it happening. And so you get the same advantage to that theory without having to buy into eternal inflation as long as you've got many worlds on board.
Yeah, I'd have to think about that. I mean, I'll even if, I just don't know how to think about that right off. I mean, let's say I grant you that the sort of Deutsch-Wallace way of assigning probabilities works, and so then you have a sense of probabilities brought in from the many worlds interpretation. And your argument is that that sense of probability associated with single-shot inflation could mitigate the sort of worries about initial conditions problems.
By the use of kind of anthropic.
Right.
But I think we'd have to compare that to the amplitude in that wave function for just an ordinary Big Bang without inflation. And if you use the entropy as a proxy for the relative weights, it's going to be a lot more ordinary Big Bang universes than inflation or single-shot inflation.
So I was thinking I was finished at 12, actually. Is that true? Or
Yeah.
So I was going to go back into Boltzmann brains if I had more time. So I think I'll have to think about your question more. But any other questions? I didn't mean to end discussion, but I just wanted to confirm that I wasn't wrong about when we were going on. Okay, well, thank you. And,